So welcome back after our break, and I'm glad to introduce our next speaker, Pei Sun from Northwest University, who will speak about exact surface energy of the Hubbard module.
Thank you for the introduction and thanks for this opportunity. This is my first time giving a presentation in English. If you have any questions, please let me know the page number and the specific formula you are referring to, and this will help me better understand your question. Thanks again. My topic is about the exact surface energy of the Hubbard model with unparalleled boundary magnetic fields. My topic will have 4 parts. The first part is about the Bethe solutions, because this topic is based on the exact solution by using the off-diagonal Bethe method. And the second part is about the partners of beta rods, because we need to know the density of the beta rods, then we can give the eigenvalue. And the third part is about the contribution of the inhomogeneous terms, because we want to use the normal approach, so we need to know the contribution comes from the inhomogeneous terms. And the last part, we will give the analytical equation of the surface energy. Okay, let's start from the first part. Bethe solutions. What we investigate here is the one-dimensional Hubbard model with general boundary fields. Here, the C plus and C are the normal creation and annihilation operators, and T, N, and U are the normal Hoping constant number of electrons and the on-state repulsive interactions. The difference between the unparalleled boundary fields and the diagonal boundary fields is that it breaks the U1 symmetry. What does that mean? It means that the Z component of the total spin will no longer a good quantum number. So we call it the general boundary magnetic fields. Combining the coordinate and the off-diagonal Bethe methods, we can give the eigenvalue of the Hamiltonian. If you want to know more details about this approach, and you can read this paper. Here, the eigenvalue can be expressed by the Kj. Here, Kj should satisfy the BES. Here, we mean the inhomogeneous Bethe equations. The inhomogeneous terms will become zero under some special boundary conditions. For example, if the boundary is diagonal, or you can see the parallel boundary condition, then it will disappear. And if you want to know more details about the off-diagonal Bethe method, and you can read this book, the off-diagonal Bethe for exactly solvable models. And in this book, there are many one-dimensional spin checks with general boundary conditions. And in this book, they give the exact solution of the eigenvalue and the eigenstates. Next part is about the partners of beta rods. Just like the last part, we need to know the distance of the beta rods. So here we consider the partners of the beta rods. Firstly, we need to consider the singularity of the BES. Here there are 2 singular points. The first critical point is module of H equals to 1. H is the boundary parameters. And if a module of H equals to 1, then the BES will behave like the periodical structure of the scanning process. And the second singular point is h0. And of the module of h equals h0 here, then we can only see that the BES will behave like the free open boundary, because in the BES the terms like this in the red circle, all the boundary terms in the second BES will disappear. So based on these two singular points, of course, we need to combine the numerical dates. For example, when when the number of lattice equals to, you can choose 4, 6, and 8. And then we can conclude that the boundary parameters can be divided into 5 regions. Here we note that the value of the critical field h0, the second critical point, will vary with the on-state coupling U, and it's always bigger than 0. Here we give the partners of the beta rows in different regions. And you can see that there are 2 cases of the beta rows. One case is that Kj is real, and the next is that it will connected with the boundary parameters. We call the beta rows connected with the boundary parameters the boundary strings, or somebody call it the boundary bound state. So why we expect the partners of the beta rows would be different in different regions? Here is the principle. Because the boundary parameters appear in the BES equations, so we expect the beta rows can be connected with the boundaries. And we found that under some special boundary conditions, of the beta rows is a complex number. Then on the left-hand side of BS, one term should tend to infinite or 0. Of course, we use a thermodynamic limit. And then on the left side of the BES, it must also tend to infinite or 0 to keep the BES hold. For example, here, under one kind of boundaries, of the beta rows equals to lambda m here, and the first term in this BES will become 0, and the second circle will become infinite, of course in the thermodynamic limit, and then this beta rows we can call it a right beta root. So we expect the partners of beta rows would be different. Next, we will talk about the contribution of the inhomogeneous terms. Why we consider the contribution of the inhomogeneous terms here? Because we want to give the analytical equations of the eigenvalue, and of the beta SS equations has additional inhomogeneous terms, and we can't use the normal approach. So here, firstly, we consider the contribution from this term. We define the delta E equals to E minus E homogeneous. How we can give the dates E, and you can choose randomly the boundary parameters, and then here we use the DMRD in Altizer software, and we give the exact eigenvalue. Then you can give the value of the E. And next, we should give the equivalent parental boundary fields. They share the same module of H1 and Hn. Then we give these 5 pictures show that the contribution of the inhomogeneous terms will appear in the red circle, which means that 1 divided by n. And the dates show that what we want to know is the surface energy, the EB. We don't need to know the contribution from the next order. So the data show that we don't need to consider the contribution from the inhomogeneous terms. So in the next part, we ignore the inhomogeneous terms. We use the equivalent parallel boundary fields. I should mention that equivalent parallel boundary fields, not random parallel. Now we know the distribution of the beta roots, we can give the surface energy using the normal approach. We call not we call the method is the Yang-Yang approach. By using the Yang-Yang approach, we can obtain the density of the beta roots. Here, what in the red circle is the contribution from the bulk of the spin trace, and the others are connected with the boundary parameters here. Then using this approach, the ground state, of course, in this approach, it needs the quantum numbers and the Fourier transformation, and the ground state energy and the surface energy can be given. In the first part, it's the same as the periodical boundary conditions, and the second part it comes from the boundary parameters. We also compute the surface energy using the DMRG in the ITER software. The results depicted as the red stars. Red stars is the result of the DMRG. And the analytical expressions are represented by the blue curves. This paper is the archive number is this paper, and you can see that the analytical expressions are totally same as DMRG, or you can see the ITER software given. So here we can see that our restaurant is right. And there is another question here. Is it really reasonable to ignore the inhomogeneous terms? Because we just based on the DMRG results, we don't talk many about it. Here there is another paper analyzing the distribution of the zero roots of the transformatic. The transformatic connected with the beta ansatz method. And by using the transformatic, you can give the exact eigenvalue. And they prove exactly that, not by using the dates, but exactly the inhomogeneous terms contribute really nothing to the surface energy, to the leading order. And if you are interested in it, you can read this paper. Here we should also note that we ignore the inhomogeneous terms because what we want to know is the surface energy in the thermodynamic limit. If you are interested in the eigenstates of the system with nonparallel boundary magnetic fields, they will totally different from the equivalent parallel ones in the thermodynamic. And the boundary magnetic fields can affect the spin configurations of the electrons in the back. And there are some other papers talk about the eigenstates. So the eigenstates are quite different from the parallel boundary fields. So I will stop here and thank you for your attention.
Any questions?
I just wonder about your information about solutions to the Bethe ansatz equations for Hubbard model. You wrote many equations, and it looks very, it's maybe related with the so-called Takahashi Suzuki model.
Can you repeat the question in the microphone, please?
I just wonder about what you can say about solutions to the Bethe ansatz for Hubbard model.
Solutions.
Do you study it for finite chain or for infinite chain?
This is a solution of the Bethe ansatz equations. Firstly, we want to know the particular bit rules. We choose some special boundary conditions, and we give this table, and then we prove that although the table comes from the special boundary conditions, and the distribution of the particular bit rules are also right for all the boundary conditions. We prove that it is right because you need the numerical results to give this table. So we choose some special, and then we prove that it is right for all the boundary conditions.
Yes, it is analysis of Bethe ansatz equations, but what is the output? What can be said about structure, about number of solutions and similar things?
The number of solutions.
The number of solutions, given this table, the number of solutions is 4, 6, and 8.
Okay. Okay.
And my question is linked to the previous one. It's also about the slide. So this is the structure of Bethe roots as a ground state, as you have written, and this looks like some miracle that they are situated in one. They are all real, and so they form like some smooth curve at least. Since the Bethe equations in Hubbard model don't look exactly like Bethe equations for x6 model or something like that. There is a difference in powers in left-hand side and right-hand side. And so, have you studied, maybe numerically or not numerically, how Bethe roots are distributed, maybe in thermodynamical limit, for not only ground states, but for other states also?
What? Can you speak slow?
Have you studied the distribution of Bethe roots in not only the ground state? Do they form some smooth curves, or do they rely on some form some amoebas or something like that? So it's
You mean not ground state? Yeah, the herald will seem as periodical, so we didn't consider it because you mean the excitation, right? The excitation will seem as periodical, so we didn't talk about it.
okay. And maybe one more question. So it's when you solve these equations, and maybe Grace's next slide, you tell something about yes, compensation of singularities. And so it's only about the last root or about what? Because there is some complicated process of compensation, zeros and infinities. And so it's, as far as I know, it's for many people, it's an interesting question how to deal with such singularities. And so is it written somewhere in, let's say, in full form, so where one can find out the derivation or some analysis? So where one can find about this technique of obtaining Bethe roots via this compensation of singularities, like this how to say this way that the infinity from the left hand side have to when the number of multipliers in the one side is large, so we have to go to poles of the left hand side. And so is it yours or is it somewhere written maybe?
So sorry.
Reference for this analysis.
Reference. Maybe you need to read a bit about the x spin check. Maybe it's easier because the Hubbard model is a little complex. The Heisenberg with general boundary conditions. It also has Bethe ansatz equations with general boundary condition, and it only has one BES, and the Hubbard model it has two BES, so the beta roots are connected with each other. So we need to consider combine this, and the Heisenberg model will be easier because it only has one BES, and you can understand how we can give the string solutions.
Oh, okay.
Okay, thank you very much. Let's thank the speaker.
Thank you.